In the previous video, I started analyzing data from a between subject and within subject design. That is a mixed design. And we got as far as the place where we need to now do omnibus inference. And so we have to check our assumptions first. To check the normality assumptions, we're going to calculate the residuals from a model and look at the normal QQ plot. One of the things that I mentioned earlier on is that if we go ahead and put in all the variables in our model and then look at the residuals, that is a conservative check for both the normality of the between subjects factor and the normality of the within subjects factor. So that's what I'm doing here. This is actually not the model that we're going to use when we look at the analysis of variance, but it is a model that will allow us to get out the residuals after accounting for all of the factors. Now, what I've done here is I've put in time by treatment as one factor. Remember, whenever you put in the interaction, that the main effects are automatically included in the model. So this is a shorthand for saying put in treatment, put in time, and put in treatment by time. Remember, treatment is a between subjects factor, time is within subjects, and treatment by time is also within subjects. But we have one other thing we need to put in this model, and that is we need to put in the ID numbers. Why do we put those in? Because that is going to remove the residual due to the variation between individuals. That is, we're looking at the variation that occurs between individuals, which you need to do. You need to remove when you look at within subjects factors. And we have within subjects factors in this model. So that's the extra little tricky piece here. Now, this is, again, not the model that we're going to use, but it's a real easy way to get out the residuals we need in order to check normality. So again, the within subject factor by the between subjects factor, and then take out the between subjects themselves. So let's go ahead and run this. And oh boy, we have, it looks like, over dispersion. We have substantial amount of over dispersion. Notice that we have larger than standardized residuals starting at about a z-score of 1. So this is giving us a heavy tail here in the right side of our residual plot. And then we have the absolute value of our standardized residuals are actually bigger also on the negative side. That is, when I get to negative numbers, I have even smaller negative numbers or bigger in absolute value numbers. So on both tails, I have heaviness, and that's over dispersion. Over dispersion is probably the worst case scenario, because what it means is that when we set our critical value using the normality assumption, which is what we always do, when we set that critical value using the normality assumption, there's actually more area in those tails than what we had figured was there when we set those critical values. So without switching to more advanced methods, such as multivariate methods or non-parametric methods, without switching to those methods, about all I can be left to do here is to mention over dispersion in my data and state that my type 1 error rate could potentially be bigger than what I'm actually setting my maximum allowable type 1 error rate to be. Remember also that we have 8 women measured 5 times, so that gives us 40 data points. And I would say for this level of over-dispersion that 40 is not big enough to be able to say, oh, by the central limit theorem, I'm okay because my sampling distribution is going to be normal. I would have expected for this amount of over-dispersion, or I would want for this amount of over-dispersion to actually have a much bigger, maybe at least twice as big of a study as what I have. And maybe that's doable. I mean, they're doing this study with only eight ladies. Maybe they could have used 16 or 20. Okay, so I'm sorry to say that I haven't met the conditions for normality. Now let's check on sphericity. I mentioned that we were going to be using the long format for just about everything, and this is the one exception. To use the wide format makes it easier to check sphericity because we're taking differences of pairs. So you have seen me do this in a previous video on within subjects design, so I'm not going to spend any more time on this. It's really nice in this video series. We're putting together concepts from previous video series, so all I'm showing you is how they come together. But we're creating all possible pairs of difference scores, and that led us to 10 different pairs. And so I'm then creating a number for each of these, and then I'm going to plot them, and I get a plot here. And reviewing this plot, again, I'm doing these difference scores, and each of the difference scores is based on just 8 individuals, so I only have 8 points here, and that may not be very good stable estimates. I do see here in this very last one, it looks to have substantially less variation than, say, here at number 1 or number 0 and number 4. This is actually, I guess I defined it as difference 1. So here at number 1 or number 4 looks like a lot more variation than, say, at number 9 and number 10. So this also may be a bit of a concern. So when you have not met the conditions for valid inference, you at the very least need to warn the readers. A better case scenario is to learn advanced techniques that are robust, that allow you to handle such situations without such strict conditions for valid inference. So now that we've done the normality check and the sphericity check, let's go ahead and get our ANOVA tables, which are not going to give us correct p-values, we've already determined, but let's go ahead and get these. Here's the actual model that we're using, and it's going to have 2 error terms in it because we're really going to split this up into 2 analysis of variance. One of them is between subjects, and that's the first part. So in the first part, you notice that I have the response measure as a function of the between subjects factor treatment, and I want to use for that residual for that, I want to use the variation between IDs because IDs are independent of each other. They're between subjects. So I'm going to use the residual, what's left over after taking into account the 2 treatment conditions. I want to see what's left over in terms of the variation among IDs. So that would give me the between subjects part. The within subjects part is going to have several components here. I'm taking treatment by hair, which is interaction. So that's going to give me a within subjects. I said treatment by hair. I'm sorry, it's treatment by time. I saw the word hair there. It's treatment by time, and that's going to give me a interaction, but it's also going to give me the time effect because that's also within subject. And then what about the residual? Well, that's everything that's left over. Everything that's not in our model after we've already taken care of the between subjects error, after we've already taken care of the between subjects effect, and after we've already taken care of the 2 within subjects effects of time and time by treatment. And so let's run this and take a look. Here you'll see ANOVA table 1, which is between subjects, ANOVA table 2, which is within. The between subjects has been removed, both the residual and the effective treatment. Now remember, I'm not interested in that effective treatment. Why not? Because if I looked at the effective treatment, it would be averaging across the weeks, and that makes no sense. Similarly, I'm not interested in this effective time. Why not? Because that would be averaging across the two treatments. And that doesn't make sense to look at the difference in times averaged across the two treatments. What I'm interested in is, was there an interaction? And when I look back up at that plot right here, which really is the primary plot we're looking at, to look at an effect, it looks like there is an interaction, that Rogaine actually did help increase the amount of hair for at least the first 16 weeks, and then it stabilized, and even when stabilized, it stayed above. It didn't come back down because they continued to take Rogaine. It stayed above the placebo effect. And so when I look at this to see, can I infer that? The answer is yes, I can. I have a p-value of 0.02. Now, maybe that p-value shouldn't be 0.02. Maybe it should be 0.07. Remember, we did not meet the conditions for valid inference. So that would make me a little bit concerned. But nonetheless, I do have a suggestion, both from description and from this rough inference, that Rogaine is probably helping, and I may be able to infer that to the population, though I, quite frankly, at this point, I'm ready to encourage the researchers to try a larger study to stabilize things and to also take care of this normality problem and see if, in fact, they get similar results with a larger study. All right, so that's the omnibus analysis. What null hypothesis am I rejecting here? I am rejecting the null hypothesis of all the possible tetrad interactions all being zero. In other words, I'm rejecting the null hypothesis that there is no interaction. That's the null hypothesis. And I am finding that there is an interaction. And I've done that with the omnibus test, but the next thing to do would be to maybe look for specific tetrad comparisons, as we've done in past videos, to see if we can say, hey, here's something that's interesting to me. I want to know, by week 16, can I say that I have a difference? Because it sure looks like it from the graph, but can I infer that? That would require those tetrad confidence intervals. So let's look at those in the next video.